So welcome back. So now we are going to be using MapReduce in order to build the standard inverted index, and hopefully you will find it as fun as hunting Pokemons. We'll see. So here's the major difference. No, let me start with the resemblance. The resemblance between MapReduce and SPIMI and BSBI. They are alike in the sense that we will also have batches. We have a collection of documents and we cut it into batches, right? Mathematicians call it a partition, right? A partition of a set is just many subsets that do not overlap and their union is the whole set. That's called the partition. So we have a partition of the entire collection, and each one of the partitions is called a batch. So this is the same, but there is a difference. The difference is that in BSBI and SPIMI, the batches, they are all stored on the local disk. It's all fitting on the disk, you just process them sequentially. In MapReduce, the difference is that the batches might not be on the same machine. In fact, they might be all over the cluster. You might have 100 machines or 1,000 machines, and the batches of the documents are just all over the place, right? So this is why you can actually have more than fits on a single machine. But apart from that, the idea of processing in batches is exactly the same one. But of course, we will do it in parallel with MapReduce. All right, so this is what we want. We would like MapReduce to spit that out of this input right here, the collection of documents organized in batches. All right. I'm just throwing words at you, but don't worry, these are all synonyms. Here I call it shard. A shard is the same thing as a partition, is the same thing as a block, it's the same thing as a chunk, it's the same thing as a batch. These are all synonyms for the same thing. It's just that several people might call it differently, but this is all the same, right? Shard, block, chunk, partition, batch, all the same. So we shard the collection of documents, we create our batches like this, but these batches might be on different machines. All right. Then we have, here I'm doing something that I completely forbid in the big data lecture. I tell the students, do not do that. Do not call it mappers, do not call it reducers and so on. You have to be more precise. But here I'm not teaching big data, so this is why I allow myself to kind of do it using these shortcuts. So I'm just going to call it mapper and reducer. So on the mapping side, we take these documents, in that case, 2 documents. Of course, in a batch, there's not only 2 documents, there's probably more like 1,000 documents or 1,000,000 documents. But let's imagine there's only these 2. Then this is called the map function, is going to take these documents and output my term document ID pairs, right? So I have ETH1 because there is the word ETH in the first document, document 1. Then there is the word computer in document 1. So I output ETH1, computer 1. And again, 1 is the document ID of the first document. 2 is the document ID of the second document, right? Then I know that there is the word CPU in document 2, ETH in document 2, and so on. Again, I insist, these are not counts here, right? For the Pokemons, we had counts. We were counting the Pokemon. Here, these are the document IDs that I have on the right. So my key is the term, and my value associated with it is the document ID. Okay, this is the mapping function. Everybody is following? Okay, it's complex today, right? We are getting deeper, so I want to make sure everybody is following. Okay, and then on the reduce part, the reducer, so technically that would be the reduce function that I'm showing here. We get all of these key values that we got from the mapping site after the shuffling, and I have here all of the pairs that have information on the left, right? So I see that information is in document 1, 2, 4, 5, 8, and 9. And so I'm just getting all of these pairs coming from the mapping side. I'm responsible for information as a reducer. Reduce slot would be the appropriate word. And then I merge all of these pairs, term document ID, into one row of my standard inverted index, right? So now I have the term information, and I create the postings list 1, 2, 4, 5, 8, 9. So obviously I need to sort here. There's some n log n, but at the level of 1 term. And then I add also the document frequency because we also need it in the output. That would be 6. There's 6 of them. So you see, out of the reduce function, we spit 1 entry in the standard inverted index. Right? For whom is that clear? All right, so you see the mapping side, where we take the documents in a batch and generates these term document ID pairs, and the reduce side, where we take the term document ID pairs and generate one row of the standard inverted index for each term. So again, I repeat, because we were discussing during the break, it might be that the same, I'm not going to say person because now it's computers, but it would have been the same person in the class experiment. The same person, the same reduce slot can be responsible for several terms. It might be that this reducer is responsible for information and also for computer, but it's still one after the other. We first create the posting list for information, and then we create it for computer, right? Just that it can also be assigned more than just one, but it's still one term at a time. Okay, and then if I have done that, so as you can imagine, I'm doing all of that in parallel, right? On all the machines, I'm just generating my term document ID pairs. Then the shuffling means all over the network. So here you ship all of these pairs all over the network, and in such a way that all the ones that have the same term will land on the same machine. And then on that machine, you create the row, and you finally get the end results. Okay. The architecture of MapReduce, again, this is big data, so you don't need to understand much, but basically the idea is that we have some sort of distributed file system that everybody can read from and write to. And the trick is that it's called bringing the query to the data. We make sure that the computations are done exactly where the data is. So basically, wherever the documents are stored, on the same machine where the documents are stored, I'm also doing the computation with the local CPU of these pairs. This is what is meant with bring the query to the data, right? We just try to do everything locally to minimize data shipped over the network. But of course, when the shuffling time comes, then you need to ship everything over the network. Okay, so this is yet another scary slide from big data, but all I'm saying here is that block is a synonym for batch, is that we have this batch of documents that are stored on this file system, and every one of these batches corresponds to one execution of the mapping phase. Okay. All right. So the tricky part here for me explaining MapReduce is that, of course, in the big data lecture, I'm spending 2 or 3 hours explaining MapReduce here, right? But of course, I don't want to do this here. So this is why here I just wanted to show you the high level of how this is done with the Pokemon intuition. We are not going to ask you to actually implement this. And if you are interested in going into the details of MapReduce, more in details, and understand how this all works with the distributed file system, then you can come back in fall for big data. All right. But I hope that you have an intuition, which is my point in here. So what we have managed is we managed to build a standard inverted index of the entire internet, technically, right? So a search engine is going to download the entire internet to their machines, cluster of thousands of machines. And like this, in parallel, they are going to create these intermediate key value pairs and then create an index. This is the reason why when you open a search engine and type something, you get an answer within milliseconds. That's because of this, because an index was built like this with something that looks like MapReduce. Now you know the secrets of how comes that search engines are so fast. All right. Any questions so far before I move on to the next part? Not in the room, on Zoom, any questions? No questions on Zoom? Okay, don't hesitate, right? You can also come to us offline if there is anything. Okay. So now the transition to the next part, why online? For BSBI, SPIMI, and MapReduce, they had something in common. It is that we just downloaded an entire collection and then we indexed it. That's called offline indexing, right? We download a snapshot of the internet, then we index it. But of course, as you might imagine, the internet evolves, keeps changing. People create new pages, people change pages. If you are in a library, you keep buying new books. You might also let's not say dispose, because I don't like to dispose of books, but at least archive or put in the archives of the library. So basically, the collection changes all the time. This is a completely different use case. How do we handle it if the collection keeps changing? We cannot handle it just in the way that we've done it before, because that was assuming that the collection was frozen. It was just what it was without any evolution. So now we move on to online index construction. And again, here I'm going to give you a few ideas and techniques that are used in order to deal with the case that the collection keeps changing all the time. So first, imagine that you want to build your search engine and you want to start indexing the whole internet. Well, you need to first maybe do it once, right? So you're maybe going to just crawl over the internet once, download everything, and then build your index, right? Then you have a snapshot. Today, March 31st. Oh, that's actually backup day. Don't forget to do a backup of your machine. So March 31st, 2023. And I have my index for this snapshot of the internet. And then the internet continues to evolve and somebody added web pages somewhere, right? So obviously they are not in the index yet. What can I do about it? What I could do naively is just I crawl again over the internet once and rebuild the entire index, right? It will take time. It takes time to actually do that, right? But this is one way of actually doing it. And then we just keep periodically reconstructing our index for the entire internet, right? And again, and again, and again, and again. The problem with that is called staleness, is that while you are rebuilding a new index, people using your system will not see yet the new changes. In real life, an estimate of the time that it takes is 48 hours. Typically, when you create a page, you have to wait for 48 hours to be visible. This is called staleness, right? It might actually have evolved. Maybe now it's less than 48 hours, but I remember at some point that was what is assumed. So this is one problem, right? While you are reconstructing the index, you're not yet serving the new pages. But there is another problem, is that you are consuming resources from your cluster in order to build that index. You're consuming CPU, you're consuming storage, and all of these resources, they are not going into serving the requests of your clients, of your users. So that might actually slow down the entire system. And in fact, that's not just true for a search engine, it's true of a relational database, right? If you create a relational database with PostgreSQL, for example, and you build an index in the background, the whole thing is going to be slow. If people try to execute queries, it will be slower because some of the resources are taken by the index construction, right? So these are some of the drawbacks of doing things in this way. So then, over the past 2 decades, I would say maybe a bit more, even before search engines, this was already done probably in libraries, people found solutions. One solution is that if there are updates to your collection, you don't touch the index that you built in the past, you just keep it as it is, but you just put the new books or the changes into some other index in memory, that's called the auxiliary index. So basically, everything that is old is just frozen in there. You don't even touch it, it's on the disk. And everything that is recent, you just have it in memory in the auxiliary index. So now you have 2 standard inverted indices, right? You have one that is for the old data and one for the more recent data in your memory. And that means, of course, since you have 2 standard inverted indices, when a query arrives, you need to do 2 lookups, one for the old data and one for the new data, right? So it's a bit more effort, but this is probably fine, right? So you're both looking, you're looking in two indices. Now, if you keep doing that, there's new documents, new web pages created, and you keep adding and adding and adding and adding data to your auxiliary index, at some point, the auxiliary index is going to become gigantic, right? So what you do is that you merge it periodically, I don't know, every 2 days, every week, every month. You merge the auxiliary index to build a new old index on disk. How do we merge? We know how to do that, linear time. It's pretty much what we've done before. So merging, we know how to do, and we know that it's in linear time. So we just merge periodically when the auxiliary index is too large, or maybe every week or every month, right? So here I'm just merging, there you go, right? Linear time. Okay, now, one way to organize things, for example, if you want to merge efficiently, is to say that the way you organize things on disk, you could say that every one of these posting lists, every term and its posting list is one file on the disk. This is one way of doing that. And then when you are actually adding postings, since it's new pages, it's new document IDs, then you just append to the files, right? But if pages get updated, then of course it's more involved, because then you might need to also modify earlier postings, but then you just rewrite the entire file. Okay, and then you have only one seek per file, because you just do it once, right? You load the file in memory, you do your merge, and then you put it back on disk. All right. Now here's another challenge for you. This is the case where we add new documents. What if now a document gets deleted? A page is removed from the internet. You cannot just add the page in the auxiliary index, right? Because then when you query both indexes, you will still find it in the old index, right? So your query is still going to return the page, although it was deleted. And the trick here, in order to deal with deleted pages, is yet an additional structure. That is, it's actually a very simple structure. It's just a list of bits, a list of flags, one for every document, and then you keep it in memory. And every bit is just telling you this document exists or it was deleted, right? So this is called an invalidation bit vector, right? Because it's just a vector of bits, one bit for every document, and you just, by document ID, you know the position of the bit for any document. And so if I delete a document, I just mark it here in the invalidation bit vector as deleted, even though it might still appear on the index on disk. And when the query arrives, you look at the data on the disk, at the index of the disk, you find all of the document IDs, but you filter that with this invalidation bit vector, and you only keep those that are actually not deleted, right? So this is where you are going to remove the documents that get deleted. So with that, you can deal with deleted documents without having to modify the index on disk, right? Just add this structure for deletion. And in fact, this is actually one of the big ideas of modern databases and large-scale databases. It's this idea that deleting is not actually deleting. It's a paradox. You delete by adding something. You delete data by adding the information that the data is deleted, right? So this is a very common pattern. And then, of course, the next time you do the merge, in 2 days, in 1 week, and so on, then you can apply these invalidation bit vectors to actually remove from the newly generated index everything that was deleted. Who is following? Okay, so you see the IDs in there, right? The first idea is to just rebuild every couple of days, you just rebuild everything, right? You just rebuild. The second idea is to have an auxiliary index in memory, and then you look up on both, right? Then you merge periodically this auxiliary index, and you deal with deletion with these invalidation flags that filter out any of the documents that might have been deleted when you actually look up in the index. Right? Okay. Now, in practice, if you have one file per posting list, it might not be very efficient, because if you index the entire internet, the number of terms is going to be gigantic. We will see the relationship again with the number of terms compared to the collection in the next section of the course. So in index compression, there is a relationship. But basically, as you can guess, this relationship is monotonous in the sense that the larger the collection, the more unique terms you're going to have, right? So this is a problem, because then if you end up with 1 million files to modify every time, there's latency for every one of them, so it actually takes time, right? So you have scaling issues after a while, especially if you are at 1 billion, for example, that doesn't even fit anymore on your file system, right? So on your laptop right here, for those who have laptops, you might have 1,000 files, maybe millions of files. I'm pretty sure you don't have billions of files. That wouldn't fit. But you might have on the internet 1 billion terms. That's absolutely possible. So what you do is that you have this slider that you can put, and that's basically a design choice. When you design the system, you can decide to either have a granularity that you have a lot of files that have less terms in each, or you have the other extreme, which is one single big file, right? But of course, you have also in the middle that you can have several files and each file has several terms, right? In fact, this is again a partitioning that you are doing. You're essentially partitioning the terms, and each partition here is corresponding to one file on the file system. Okay. Following still? Okay. So now I'm moving on in terms of improving the whole thing. So let's come back to this idea of the internet gets updated, people create new pages, and you have this auxiliary index for the fresh data. And let's say that every week you merge this auxiliary index into the big index. You do it 1 week, 2 weeks, 3rd week, 4 weeks, just every week for a while, you do that. So the pattern that you will start seeing, if let's say the threshold at which you start merging, that corresponds roughly to a week, is that you have n postings. Let's call it n, small n. That would be the threshold of the number of postings in your auxiliary index. And if you reach that threshold, then you merge. So you're going to have a first merge of n postings. You're going to have a second merge a week later of n postings, and so on and so on and so on. And then t over n weeks later, you're going to have another merge of n postings. T, what I'm calling T here, would be the total number of tokens over, let's say, 10 weeks, right? So the total number of tokens I'm ever going to see over 10 weeks. In the first week, I'm just getting started. So I have a first merge with n posting, then another one, and then the final one, T over n. Maybe it's easier. I mean, this is what I do in this case, is to not get confused. I just imagine made up numbers. So let's say that, for example, T is 1 billion, right? So we have in total T that is 1 billion terms, 1 billion tokens in total. And imagine that each one of my auxiliary indices, I merge it after 1 million tokens, right? So I have 1 billion in total that are going to come over my weeks. And every time I have seen 1 million tokens, I just merge. So n would be 1 million, T would be 1 billion, T over n would be the division of that, 1,000, right? So if I have 1 billion tokens in total and I merge every million, then in 1,000 weeks, probably going to take a few years, but in 1,000 weeks, I'm going to have merged everything, right? So T would be 1 billion, n would be 1 million, and T over n would be 1,000, right? So I will have merged 1,000 times every time that I have 1 million new postings. Does it help? It usually helps me to put numbers in there, right, or to understand the letters better. Okay. So what's the complexity now? Well, we saw it's linear, but linear in what? Linear in the size of what you are merging. So obviously the first time it's O of just n, so that's 1 million postings that you merge because the index was empty. But then the second time you're merging n with n, right? Because there's an existing index on disk with 1 million postings, and then you have 1 million new postings. So now you have 2 million postings. So you see now the complexity is 2n, right? And then finally, every time 3n, 4n, so the size increases. And at the end, the complexity is 1 billion, because then in the last merge, I just have all of them, right? So of course, the constant normally would not be relevant, right? 2n is the same as n, but it is relevant if I do it 1,000 times. Then I need to actually care about this constant in front of the n. So I have basically n plus 2n plus 3n plus 4n all the way plus t over n times n, right? So t. So let me remove this toolbar. I know how to do it from the trick that I open the chat and close the chat and then it's gone. There you go. So we have basically every merge is going to take more resources than the previous one, just because I have more and more and more and more data. So if I add everything up, n plus 2n plus t over n times n, is basically you can compute it. You know the sum of the first n integers? You learned that? N plus 1 over 2, right? That's exactly what we do here. So 1 plus 2 plus all the way to t over n. That's basically t over n times t over n divided by 2. So the complexity would be t squared over n squared, but we multiply with by n, right? So we have t squared over n. Who understands how I come from here to here? Okay, very good. Of course, it's a complexity class, so I don't need the 2 or the 1/2 in front. Okay. So the analysis is this, that if I look now, the whole resources for keeping merging and merging and merging increasing amounts of data, this is going to be quadratic in the number of tokens. We don't like that. Imagine it's a billion. Now you have a billion squared, right? This is enormous. I think it's probably a quintillion or something, a billion squared. That is a billion squared. I think it's a quintillion. So this is a lot. This is not acceptable. It doesn't work. We just cannot do it in this way. So this solution that sounded like a good idea to merge regularly the auxiliary index into the index on disk doesn't scale. The complexity class is something that we don't like in big data. We don't like quadratic, right? We love linear. We are kind of fine with n log n, but quadratic for large scales, that's already something that we are scared of, right? So can we do better? Yes, of course, we can do better. I'm about to show you how we can do better. And it's actually a very nice idea that is very popular and important in modern database systems, and not just for information retrieval, but this is also something that is relevant in white column stores, in large-scale databases. So yes, we can do better. Can I do it in 15 minutes? Probably. I think I will manage in 15 minutes. All right. I prepared an animation because I love animations, and I think it's the best way to actually understand the trick to do it better. So here it comes. I start at the very beginning, right? So I know that I will have a billion tokens incoming maybe in the next few months, and I start indexing the documents that get created, and I have originally a single index that I'm building on day 0 that has n postings. Let's say 1 million postings, n postings. Okay, it fits in memory. That's nice, right? So all the way to 1 million. And then I reached that size of 1 million that I told myself, okay, if it reaches 1 million, I need to just put it on disk. So I'm going to just put it on disk, right? I'm merging it with an empty index. This is what I'm doing, but merging with an empty index just means copying over to disk, right? So now I just put my million postings right there on disk, right? I just call it Z0 here and I0 when it's on disk. Okay. So far, so good. Right now, it looks exactly like what we've done before, right? So then we continue to ingest the new pages that come, and now we have this auxiliary index in memory, also as before, that we start filling. And then at some point, we reach the entire memory. We have 1 million more, right? And we saturated the memory. What do? We merge into the two indices together. Now we have 2 million postings, and we put it back on disk, right? Now you're going to tell me there's nothing new here. This is what we've been doing all along, right? We just merged the auxiliary index on disk. Yes, but now comes the difference with the super clever trick to get rid of the quadratic complexity. Now I continue to ingest new pages and new documents that come. I continue until the memory is saturated. I again have 1 million new tokens. And now normally what I would have done before is I would just have merged it into the 2 billion on disk and have gotten a big index with 3 million, right? Before, that's what I would have done, right? Every time I just add 1 million. But no, we are not going to do that. Instead, I'm just going to, instead of merging, I'm just copying over that million tokens, so this index with the million tokens on disk. So this is the difference. Now I have 2 standard inverted indices on disk, 2. Before I only had 1, now I have 2. Right. So I0, there's 1 million tokens in there, n. I1, there are 2 million tokens in there, 2n. Okay. Who's following? Okay, so this is where the difference starts. Now I continue to ingest data. There's another million tokens that arrive from new web pages, and it accumulates in memory. Now I have 3 indices, right? I have my 2 indices on disk, one with 2 million, one with 1 million, and then I have my auxiliary index in memory. Right? So now memory is full again. I have a million token, so I'm going to merge it with I0, so 1 million and 1 million. I'm merging it to a new index of 2 million tokens. But now I have 2 indices in memory and on disk with the same number of tokens, 2 million and 2 million. So I'm merging again to one new index with 4 million tokens. Do you see the powers of 2 now that start arriving? This is the trick. So now we have an index with 4 million tokens, standard inverted index, but we are back to just one index with 4 million tokens. And then we continue. I have again now a 5th million of tokens that are incoming. But now I'm not going to merge when the memory is full. I'm just copying it over to disk. Then I have again a 6th million. Now I'm at 6 million. Now I have to merge it, of course, to an index with 2 million tokens. So now what do I have? I have 6 million tokens in 2 indices, one index on the disk I2 with 4 million tokens, and an index I1 with 2 million tokens. And now, in order to understand and map it easily, it's just a representation in base 2 of 6, right? 6 in base 2, what is it? It's 4 plus 2, right? This is exactly what's happening here. 6 is 4 plus 2. So we have an index on 2 and on 1 and nothing on 0. And then if I have a 7th million that arrives, then I just put it on disk. And now that's the representation in base 2 of 7, right? So 1, 1, 1, and so on. Do we have a question on Zoom?
Yes. The arrow of merging is drawn. The arrow of merging is drawn to the main memory. Isn't main memory full? Can we merge in there?
Oh, you are right. Maybe that's something that I didn't think through when I did my animation. So of course, yes, when it starts growing and it exceeds the memory, I should slightly adapt the animation. You are obviously not going to be able to load the 2 endpost things in memory because that's more than that. But you know how we do it? We merge on this. We can do it with parallel pointers, right? As I've shown before. So you're absolutely right. So thank you for pointing this out. I should probably adapt a bit the animation to make this clear. I was just a bit casual in the way that I did it here, right? So you're absolutely correct. Whenever I show you that I merge like this or like this and like this is actually done directly on disk as merging 2 files with parallel pointers. That is what is meant there. Yeah, thanks a lot. Okay, so now I have 7. Yeah, and now I have 8. So now I merge, and now I get a single big index. So I just stop the animation there, but you can continue. There will be a single big index of 8 million tokens. So again, it's the representation in base 2, but just mirrored, right? So you need to read from the right to the left instead of the left to the right, right? For example, if you have 6, if I come back to 6, this is 6. It's 110, 6 in base 2, right? So 110, you need to read from the right. 1, 1, 0, nothing on the left. Okay. So you're basically counting in base 2 in terms of the pattern of the indices on disk, and you only have indices that have a size, a power of 2. That's the trick. So how are we doing with that trick? Did we actually improve things? Well, let's see if we improved things. So now I have an index potentially with n postings, with 2 n postings, with 4 n postings, with 2 to the power of k n postings. So how many indices do I have? Well, if you think a little bit, it's basically going to be the order of magnitude of t over n, right? The logarithm of t over n, right? The reason is simply that if you add n plus 2n plus 4n plus 2 to the power of k n, that's basically the same as 2 to the power of k plus 1 minus 1, right? So when you add all of the powers of 2, you just get more or less the next power of 2 plus minus 1. So this is why if you now look at the total number of tokens and the size of one index, t over n, that would be the number of batches that you would have had for the previous technique, but now we are down to the log of that. Right, so the number of indices, it's basically, when I take the log, it's exactly like saying if I have an integer, the number of bits in base 2, that's the logarithm of the number. For example, if I look at how many bits do I need for 64, well, I need 6. It's the logarithm of 64 in base 2, right? The order of magnitude, always plus minus 1, because it's complexity classes. Okay. All right, so now we have how many indices? We have log of t over n, right? And so the construction time, now we multiply by, in terms of complexity classes, it's time t, right? Because it grows linearly with the number of tokens. So it's t times the log of t over n. And this we like much better than the t squared over n, right? And again, the trick is to use the powers of 2. This is the trick, right? For whom is that clear? Right? So re-look at the animations if you want it to be clear, but this is really a nice trick. In fact, there is a name for that. This is called log structured merge trees, LSM trees. And in fact, just to give you the intuition of how important it is, LSM trees. LSM trees are basically the new B+ trees, if you want, of big data, right? So you use B+ trees when you have a local relational database or when you have a local standard inverted index on your computer. LSM trees are basically the big data version of B+ trees, right? This is basically what it is. Okay. So if you want to know more about that, again, this is covered in more details in the white column store part of big data. But since it's directly relevant for information retrieval for building indices online, I wanted to share this with you. So now, what did we learn from that? Well, obviously, LSM trees are actually super important for the context of databases. However, it turns out, by experience, in the context of a search engine, so if you are Google, if you are Bing, if you are DuckDuckGo, or whatever search engine, in fact, what is done is that they actually rebuild the index every 2 days or so. Right? So every 2 days, they just crawl over the entire internet and just update their index. So it's more done like this naive way that I told you at the beginning. Sometimes it's the real world, right? You come up with all kinds of optimizations and so on, and then you end up realizing that in the end, the first idea actually wasn't so bad. And of course, there is a cost to pay for this. It is that when you Google for a new page, you will have these 2 days of delay, or maybe a bit less today, right? But you do have to account for that slight delay in the index, and that's the reason. So we've seen how to build indices when they don't fit in memory with BSBI and SPME. We've seen how to build them if they don't even fit on the disk with MapReduce, and we need to spread it over a cluster of machines. And we've even seen how we handle indices when the web keeps changing, when the collection keeps having new and new documents. We did it with the standard inverted index. It turns out that everything we've discussed can very easily be adapted to the other ones. You can do it with byword indices, you can do it with positional indices, it just works in a natural way. So this is completely orthogonal to the kind of index that you're talking about. Something important that I want to point out, and this is kind of a transition to one of the next lectures, is that all of that, the standard inverted index and everything we're doing now, this only works for Boolean queries. It's not giving you any ranking. If you query over Bing or Google or DuckDuckGo, you get ranked results. That we don't know how to do yet. We haven't seen it, right? We'll cover it in 2 weeks. Right now, what we are able to do is a yes/no. We are only able to dump results at you, but without any particular order yet. So we still need to do an extra step about that. We'll do it in a couple of weeks, right? So we cannot rank yet. The other aspect is we don't have any security considerations in there, right? I didn't even talk about what happens for cybersecurity. There are enough lectures on these things that you can take, right? So this is very common when you talk about big data systems. You leave security aside at first, and then you put it back at the end when you go to production. Okay. So the chapter that you should read especially if it wasn't entirely clear what I told you today, is chapter 4, index construction. It's the same thing I've told you today, but just explained by other people. So for some of you, maybe this will help having another perspective. Thank you very much for attending today. Today you have the exercise sessions as always. So you have the submission system for the quiz, I think at 4 p.m., right? So it stops, so you still have a chance until 4 p.m. And then you will discuss the solutions in the exercise groups. So thank you very much, everybody. Enjoy the rest of your day, enjoy the exercise session, enjoy your weekend, enjoy the Easter break, because I only see you in 3 weeks, actually, because next week is Good Friday. The week after that is the week of Easter break. So it's going to be in 3 weeks. And then we look into how to compress indices and squeeze as many space resources as we can to use less machines. All right, enjoy the rest of your day. Have a nice weekend.